here down to protection mechanisms. So we talked about all the attacks. Now we're going to talk about some of the defenses, which is, of course, the big thing about Microsoft, is that they really have a lot of defenses, and you're going to see more and more and more. That's what Microsoft did after they changed their mind in 2002 and decided security actually mattered. They've slowly added more and more and more defenses. So really old version defenses are like the non-executable stack and write or execute memory, and Canaries. Those have been around for a long time. We'll talk about them. Then there's this ideal stack layout, an ASCII armored address space that came in later, and ASLR has been around for a while, and it was all been quite effective at raising the bar on attackers. Each one of them kills another generation of attacks. And then there's heap protections, of which Microsoft has dozens now. And exception handler protections also. So the point of these, there's two kinds of defenses. I mean, one is patches that patch specific problems so they're gone, and another is where you put in a general blanket defense that kills a whole category of exploits, and that's what these are. And those are, of course, really important because they affect legacy code. So even if you're running old, buggy, crappy code, the Microsoft defense might compensate for that, and that's a good thing when it's possible. It also means that each of these defenses has a chance of breaking legacy code, and that's why Microsoft in general enables these things more on servers than clients, because people are typically willing to accept that you cannot run old crappy code on a server, but many clients, they do want to run old crappy code. Anyway, so here's an example of C code that's got a buffer overflow. Or no, this just doesn't have buffer overflow, it just defines some variables. See, the original way C was compiled, if you defined a variable and then an array and then another variable, it would just put them on the stack in the order in which the programmer defined them. And that, of course, means that if it goes like this, the 80-byte buffer, if I overflow it, it'll hit variable 1, then save DBP, then save return address, and so the typical Aleph null type exploit, you'd target return address. But even if you can't do that, I could change variable 1, and that might be enough to give me some control of the program. So that's the general structure here. So the first thing is a non-executable stack. Since memory has permissions now, in machines for more than 10 years they've had this, you can allocate a region of memory to be the stack, and you can specify whether you're allowed to run code on it, and you can make it non-executable. You can write, but you can't execute. So you can store data there, but if somebody puts shellcode there, it will not run. And when you jump to it, it will just stop, saying access violation, which is cool. Now you can still overflow the stack and change the return address. And if you do, you can redirect code execution to go somewhere else, but you can't send it to stuff you put on the stack. You could have to run to some other code that's executable somewhere. All right. And so the trick is to go to some code that already exists on the computer that is already executable. This is the general category of things that started with ret2 libc, and there are about a dozen different versions of it, where you put in the instruction pointer, a value that leads to some executable code somewhere. So if you can put your shellcode in the data section, you can return to data, and the data section might be executable. One way to get code in the data section is to just have some kind of buffer that goes on the heap, because the heap's in the data section. And so if your buffered I/O goes on the heap, you could send in some network traffic that ends up in a heap object and execute it there. That's one option. The original one that got a lot of fame was return to libc. Particularly in Linux. You would just find the location of C library objects and jump to them, because they're always there, they're easy to find, they're always the same, and that's the game there. So one limitation here, of course, is you cannot jump to every library location because you can't inject 00. Or to be more precise, your exploit, if you have a string-based exploit, which is almost always what you have, you can inject 1 byte of 0 at the end, and that's it. That terminates the string. So you can't have an address with a 0 anywhere except in the last byte that you inject. So return, yeah.
You could do that in machine code, though, right? Instead of actually calling the library function.
Not if you can't execute anything you're putting in. See, since the stack is not executable, all the injected code, you can't put in any instructions. All you can put in is an address.
Right, but when you're doing the string copy and you run into the null there, could you just use a piece of machine code to do that instead of using the string copy command?
If you can find some code somewhere that does that.
Okay.
And that's true, you can. That's right. What most people like to do is jump to library code just because they know how it works. But the alternative is, of course, to assemble it out of gadgets, where you find a pop and an increment and stuff and piece together all these little bits. And then you can, in principle, build anything, like you did with Mona. That's good. All right, so anyway, That's return to libc. Return to string copy is another one. This one's quite cute. You return to string copy. You have your exploit on the stack that won't run, but you run to string copy and use it to copy that data into a variable that's elsewhere. So that's pretty cute, because all you need is a pointer to your injected code and a pointer to the other place you want to put it, and then you call string copy and it copies that string over here. And now you've got it in a different memory segment. So I thought that's pretty cute. And that's the game here. So you've got your, before the overflow, you've got that. After the overflow, you've got your injected stuff. And then you put the address to string copy, the destination address, and the address of your shellcode. You put that on the stack, and then you'll go to string copy, pull the addresses off the stack, and then copy the shellcode that you put way down here somewhere to some other memory segment. This one is even cuter. You jump to gets. Now it takes input from the keyboard. And if you have the ability to inject input into the console, you can now type in stuff that will then be executable. So I thought that's pretty cute, but it is kind of strange. You would have to have access to standard in, or some kind of channel, which you could redirect standard in into by putting different parameters in the gets, I think. So again, that's the game there. All right, and then there's ret2 code, which is the generic container for all these. The point is you can't run any code you put in, so you put in an address, let it return, and make it jump to some code that's already there. You find code somewhere that you can run, and it could be anywhere as long as it's executable. And you can make chained ret2 code, which is what we did in that one I showed you last time with the Mona gadgets, where you have a whole series of return addresses. Go and execute a couple commands and return, and then go here and return, go here and return, go here and return. So out of these little fragments of code, you chain together anything you want. And you have to use something like Mona that will hunt through a large code base and find all gadgets that will add up to something. But that's the game. And in principle, you could do anything. In practice, the available tools that I know of only let you do a couple of simple things, like turn off NX protection and things like that. Then there's return to syscall. Remember, you can use syscall to run kernel arguments in Windows, and if you can get the arguments into the registers and then execute the syscall, then you can execute a syscall and do almost anything you want that way, ending up to about the same thing as return to libc. And then there's return to text. You jump into the binaries code itself. And this is what you did in the very first attack, where you did an attack without shellcode, where you had a thing that had a winner and loser function, and you just redirected it to jump into the winner function. You execute some other part of the code that's already there, which is fine. All right. And then you can jump to the PLT. You played with this here. The global offset table and the perceiver to linkage table are the two tables with the two levels of indirection that you go through when you execute C library functions. And if you can jump to either of these tables, you can then jump to a libc function, essentially, is what you're doing. All right. But for this one, the procedure linkage table only contains links to subroutines that are used by the program. So if you want to jump to system and execute a bash system command, but the program doesn't use system, it's not there. You can't use this technique. But you can use this one. You can jump to the dynamic linker resolver because it has the addresses of everything. So you jump here and you can now use libraries that were not loaded with the program, which is pretty cute.
Will it load them for you?
Apparently,
just presume they're in memory.
Apparently it has to be in memory. Yeah, it has to be in memory somewhere. That's my understanding. I haven't done this one. It would be interesting to get the details. All right. And so the non-executable stack, like I said, the problem is even if you make the stack non-executable, that doesn't make you safe because you can still put in a return address. So that's the fundamental error. You have, if there's a buffer overflow, you can still execute code. You just can't execute your code. You have to execute code that's already there. But that's not an insuperable barrier to success. So I've got a few iClickers. Grab one if you need one. Start new session is right. Okay. All right. So, which one is the generic item that includes all the others? guess I can quit at 25. All right, and that's of course return to code. All these involve using code that's already present in memory. All right, which one uses shellcode placed on the heap by buffered data processing? I'll quit at 25. All right. And that's ret to data. It's in the data section. Whoa, no right answers. But string copy is quite different. The data section is where heap objects go that are created if you have a buffer, like taking input. It puts them in temporary objects on the heap. And that is a place you can execute them. All right. Let's charge ahead. Okay, which one uses DIL code that the target did not load? Which is pretty awesome. Last year in one of the Linux CTFs, we did something else. There were two programs running on the same server, and one of them had the library you need and the other didn't, and you could find the address from this program and use it in the other program. That was pretty awesome. I'm not sure under what conditions that is possible, but it certainly was possible in that CTF. Anyway, so this one is DL resolve. It will go to the linker, which would have added that library, and find a pointer to it which you can use to get in the library, even though the program you're attacking didn't load the library. All right, which one injects shellcode on the stack, but then executes it somewhere else? Quit at 25. And that's return to string copy. You go here and copy it somewhere else, and then you can run it. Good, you got that one. All right. And, all right, which one reads shellcode from standard input? All right. That's, of course, gets, return to gets. Good. Okay. So, let's carry on here. All right, so we talked about this W or X, which is a pretty good idea. I used to write self-modifying assembly code in the 80s, and I just didn't know any better, but this is a terrible practice. Self-modifying code is insane. You can't even print it down, you can't disassemble it, and if you have any kind of security check, you run a security check on the code, then it modifies itself. So what did your security check mean? So it's kind of nuts. So this is pretty obvious. You only have two choices. You could either be writable or executable. Otherwise, madness will occur. So you write where you're writing data, and the executable code has to stay fixed so you know what you've got. That's the way modern machines like to do it. An early Linux implementation of this called PAX was considered very secure, but it slowed things down too much. So it was never used very much by any mainstream distribution. What has been used is the NX bit, which I understand is supported by chips on the motherboard. And so there's this is the ability of the motherboard to mark areas of RAM non-executable. So it can be done. Now you can allocate memories or regions of RAM that are writable and executable. It's not prohibited, but it is possible to specify that these are not executable, and if anybody tries to execute code here, cause an exception, an access violation exception. And like I say, this is data execution prevention. It's on by default in servers, but not in clients. The limitations, of course, as we talked about, are this just prevents you from executing the code you injected. It doesn't prevent you from executing code that is already in an executable memory segment. So you can do ret to code. And there is some memory that may still allow you to define an area with write plus execute, and there may be some memory already defined that way by the programmer. And you can use chained ret to code to write to the disk and then run things directly off the disk. That's another way to do it. There's a lot of tricks. So you can also just turn off the W or X protection. There has to be a way to turn it off, and there is, and there's a single library call called setInformationProcess that will turn this protection off. The only problem with it is you have to inject a bunch of zeros in the parameter. So you are probably not going to be able to actually make this library call if you're using a string-based attack on Windows. However, there are other library calls that don't have nulls in them that accomplish the same thing. This will change a specific region from write or execute to write plus execute, and it doesn't necessarily have any zeros. It's just address and size location. So that's pretty cute, and it's also possible in BSD. Then there's X after W. This is another trick. First, find a writable segment, write to it, then change it to execute. Now you're done writing. You don't care that you can't write anymore, then run it. So, since you can allocate regions of memory, it can be done, of course. You could also create a new region of memory, allocate a new place to copy it, they call it write plus execute. All these things are possible. That is sort of the madness of these Microsoft defenses. If you have the ability to control the execution, you can call a function that will just turn off the defenses, and I'm not really sure what they can do about that. It's like the pass-the-hash attack. People said Microsoft does these hashes, and they said, well, we have to have some token for single sign-on, and we can't think of any way to eliminate that, although it seems to me in the world of public key cryptography, they probably could think of a way to eliminate that, but what they chose is to make it harder to find the token to steal it, rather than make the token actually more secure. And anyway, so here's stack data protection. So to prevent people from doing this typical buffer overflow and hitting the EIP, there's a variety of protections. The first one was stack guard. ProPolice was the superior version replacing this, and this is stack smashing protection, and this is what you see on Ubuntu Linux. When you do a simple buffer overflow, it says stack smashing detected, I quit. Because when it tries to return, it checks to see if the canary has been altered. So you've got your stack frame is here. You're in a subroutine with some local variables, like a buffer. If you overwrite the variable, then you change the saved EBP, you change the canary, then you change the saved return address, and when you try to return, before it puts this in the EIP, it checks the canary, and if the canary has been altered, then it stops execution and says, I'm not going to use that return address because I suspect somebody's been altering it. And that's cool. This original way of doing it, if stack guard, was considered foolish because it doesn't protect the EBP. And controlling the EBP, you can use it to jump to a different stack frame, and that's almost as good as controlling the EIP. So this was considered ineffective, and ProPolice was considered better. Then the question is, what do you use for canary? The first canary was a null value, which is there so that if you try to overwrite it, you won't be able to because your stack base is what you can't put in all those nulls, so that's one option. The next thing was a terminator canary, which was even more strictly an attempt to terminate everything because it's got all the things that typically end strings, null, line, feed, carriage return, and end of file. They said probably anyway you're feeding in the exploit, you can't write those characters. And then the most modern ones all use random canaries, where it's hard to find them. That seems to be what most people have settled on as the best plan, but these are alternative ways to do it, depending on what attack you're trying to stop. The ideal stack layout, ProPolice uses it and Microsoft uses it in their /GS compiler switch. This is an attempt to reorder the parameters into a less dangerous order, which is pretty careful, because remember I talked about this back when you did like project 2 or 3, where you did an overflow from one variable into another without hitting EIP. That kind of overflow is not as common and not as dangerous, but very hard to stop because it doesn't have a chance to hit the canary. It doesn't really corrupt very much memory. So this one here is Microsoft's attempt to deal with that. So regardless of the order in which the programmer defined these variables, it takes all the arrays and puts them down at the end. So that if you overflow the array, you'll hit the canary. You can't overflow the buffer and hit variable 1 or variable 2 anymore. And so that's what they call the ideal layout of the stack. Lay it out so that the dangerous things, which are arrays, are down at the bottom where they can't hit other things. Of course, if you have several arrays, you could still overflow one array into the next array, so this is not perfect either, but it's makes it a little bit harder for the attacker. They also make compromises. One thing that really surprised me when I first started looking at Microsoft defenses is how lame they are. They tend to be implemented in a way that cuts their effectiveness in half all the time. And in particular, they never actually bothered to put the defense on all the processes in memory. So there's some unprotected processes still, even in a modern system. But that's the way it is. You have to make compromises. Windows is so complicated that you can't just change everything overnight. There's many other considerations, a giant burden of legacy code to protect, so it turns out to be a problem. Anyway, it's a, the defenses are there, but they never work as beautifully as you'd think they would work from reading the description. And like I said, the ideal stack layout has its defects. If you have multiple buffers, one buffer could overflow to the next. If you define a C data structure, a object that has buffer methods and arrays in it, that cannot be rearranged. It has to be laid out exactly as specified by the designer, because that's the whole point of C data structures. You can use pointers to them and offsets. So in that case, they cannot use this defense on you. And there are functions that have a variable number of arguments, and they can't be placed in an ideal layout because it changes at runtime. I don't know if I've ever used those. That's kind of a goofy one. All right, buffers dynamically allocated with alloc on the stack. I don't think that should be alloc A. Is it alloc A? Okay, good. I'm glad you know. Oh, alloc is in the heap. Alloc A is on the stack? I didn't even know you could do that. I've never done that.
It's not encouraging more than a simple.
What do you do it for?
Just alloc something else.
Yeah, okay. Anyway, okay, that's a new one, all right. Anyway, that would always be on top of the frame, of course, because it's allocated at runtime. And anyway, there might be something else valuable after it. The exception registration record is stored on the stack, and you can override other variables. So, you know, nothing's perfect. Every overflow has some chance of hitting something important. And this is another good one. I've certainly seen this one happen by accident in several CTFs. You can just load the libraries down at low memory, where all the addresses start with 0. Now you can't inject the null bytes, so you can't use any of that code. That's what they call ASCII armored address space. You go to address space that is irretrievably outside ASCII characters, so you aren't going to be able to inject it into strings. So it's a pretty good idea. One of the Pico CTF challenges that I've been trying to do sort of baffles me here, because it's in 64-bit code, and the addresses start with like 4 bytes of 0, and I'm like, I don't understand how I'm supposed to do this. I haven't figured it out yet. After it's over, somebody will write it up. If I don't get it next week or two, it'll be the one I don't get, and I'll wait for someone else to post the write-up. Currently, this is bothering me. Anyway, all right, so here's a Linux command. So suppose you want to execute this command, which will create a new user account, and you want it to use zeros there, I think, to make it administrator account. So what you have to do is you can make one call to system by making the last injected byte 0. That's the point here. You can inject 1 0 in your exploit, and it has to be the last byte, because that terminates the string. So it is possible to do things like things that contain zeros in a very limited way, but it's tough. I must say, Tom, you know Tom Horvath, he's working on an iOS exploit, and he told me he found a way where he can write 1 byte once, and it always has to be 0. And I said, I'm not sure I'd be able to get much good out of that. And he managed to get complete execution out of that. That's pretty cool. You just got to be tough. This is like, I'm only giving you one tool and it's a banana. Now, solve this problem. And they do it, you know. It's just a question of how smart are you? Can you do it with this one tool? Anyway, so here we're going to defeat ASCII armored address space. So here's what it looks like. You got a payload. All right, so you've got addresses there. Then you've got this, you insert the payload, which is the echo command you want to execute, which is this one. You're going to echo Gerardo and all this jazz, which will create a user named Gerardo. And then you end the command with a comment, and then you have padding, and that's the game here. So you have new frame pointer, and down here you have the pointer to system, so that this is what's going to be executed. It will jump to system, and it will, after it'll do this, we're just going to do the move, to move the EBP to the SP. That's going to happen at the end of the function. Then it'll jump to system +3 and execute that code. So that's what it looks like. And these things are not too difficult to do, but it's a significant limitation. So that's the game. You don't move the main executable down there. So if you just quit targeting the libraries, you can target the main executable, and it's not there. So that's one limitation too. All right, I got a few more iClickers about that stuff. See how they go. Yeah, grab one if you need one. So which defense puts shared code in low memory? Here. All right. like the answers are in. And that's, of course, the ASCII armored address space we were talking about. All right. So which one will cause your code to stop when it hits a knob? I felt pretty offended when this happened to me. I put it in a knob and it won't even do that.
A long time ago.
Hmm?
A long time ago?
A couple years ago. When I first taught this class, of course. Yeah. I'll quit at 35. That's what the NX stack does, of course. It's non-executable, so even a NOP won't run. That's the only defense that has this property. You can put code in that memory all you want, and when you try to execute it, it won't do anything. It will just stop and say, access violation, attempt to execute non-executable code. But I felt pretty offended when a NOP is not executable. That seemed rude. All right, so which defense uses carriage return and end of file characters? You know, I've never actually used an end of file character. The only time I remember hearing about it was with paper tape. There must be some other reason, but anyway. That's really old. That's from like the 60s and 70s. That end of file.
Magnetic tape a lot too.
Magnetic tape too, yeah. Well, old stuff. The old stuff is the best because people forget about it. And you can get away with murder. Like they hacked all the virtual machines at all the cloud services because of the virtual floppies they had, which nobody was using in 10 years, and it had bugs and nobody noticed. Anyway, all right. So here it is called the Terminator Canary. That's right. Named, I think, before Arnold Schwarzenegger had that name, but it has all terminating characters like carriage return and end of file in the canary. So which one protects the return value but not the stack frame pointer? Which is another one of those half measures that you see a lot of. I'll quit at 30. Looks like the answers are in. All right, and that was stack guard. Before ProPolice, that was what considered not too good about stack guard. It didn't protect the extended base pointer, and so you still could do quite a lot of memory corruption before you hit the canary. All right, so address space layout randomization, this really made a big difference. This held back, I think, either 1 or 2 years at Own contest. When Vista came out with this, they couldn't take it over because this threw everybody for a loop. Data execution prevention and address space layout randomization between them wiped out a whole generation of attacks. So the point here, of course, is that every process should have a random memory location. It should be unpredictable, and therefore it's very hard to tell how to jump. You have to do everything with relative jumps. Now this slows down performance, which surprised me. It sounded harmless, but the reason it's not harmless is if you have a 32-bit processor. It basically means you have to have one register permanently keeping track of the base of where you are and refer everything to that register. And that means it's going to take a few more machine language instructions to do everything, because instead of jumping somewhere, you have to load the register, add something to it, figure out where to jump, then jump there. But it also means that one register is always full, and there aren't enough registers in a 32-bit processor. There's really only a few, and having to shuttle data around all the other registers all the time slows down your performance quite a bit. In a 64-bit OS, the difference is probably unimportant. So if you want to prevent this, you could use return to gets, and then when you take the data from the terminal, you specify what location to write it to. So regardless of where your code is, it will write the data somewhere you can find it. That's one option. The other thing is to trick the application into supplying the address for you. Many applications leak addresses out one way or another, so you can find out where it is. You might find something in the register or the stack. You may remember we talked about, I think before Windows XP, one of the service packs, there was always, when you had an exception, the EBP or the EBX register contained the address of something. So it's actually, you have to be quite careful not to leak addresses out. LinuxGate.so was one in Linux systems that did this. It was a table of pointer for system calls, and some distributions always put this at a fixed location. And some early versions of Windows always put the SEH at a fixed location. So you could just trigger an exception and you always knew where that was going to be. And this remains the problem. You remember when we did the the attack I showed you last time where you ran Mona to list all the modules. It had all these modules, and some of them don't have ASLR turned on. They are not randomized. So there is some code that you can find, even in the presence of ASLR. And you just have to find a way to exploit the code that you can find. The other thing, of course, is that for some ungodly reason, Microsoft's first attempt to do this, they didn't use a random enough random number. It would seem like a simple thing to use a random number, but there have been many major exploits caused by a lack of insufficiently random numbers. It's harder than you might imagine to get a truly random number, and an enormous number of people do not realize this and write cryptographic routines that don't really use a random number. And then, of course, everything is pretty much shot. So Microsoft wrote something that only had like 8 or 12 bits of memory. 8 bits of entropy means that you have only 256 possible values, so all I have to do is run the attack 256 times if the attack doesn't crash the server. Now, if it crashes the server, it's unlikely that the administrator is going to just blithely reboot it 256 times without figuring out that something bad is happening. But as we'll see, there are some versions of Windows where it will just blithely continue under this attack and let you go. Anyway, also, you might find memory segments that are related to each other, so if you find one, you can deduce where the others are. So local privilege escalation, in order to do that, you have to find the memory. If you can get the privileges, you can go to proc PID maps and get the memory map from the system and find out where things are. So that's one cute thing. You can brute force a 16-bit value or even a 24-bit value, depending on how many attacks you're allowed to do. Remember Heartbleed. Heartbleed was scary, and it really took like 4 billion requests to exploit it, but then you got the private key for the SSH, for the SSLs on the server, so it's not unthinkable to brute force even 32-bit values for a high prize. All right, format string exploits, remember them, you can just put in a %x and it will print out pointers and let you know where things are. So you can print memory outright directly there. There are RPC calls in the Microsoft Microsoft libraries that leak out memory addresses. You get handles, and some of those handles point to objects which tell you where things are. And in multi-threaded Windows applications, if you have multiple threads in the same process, they cannot be randomized relative to each other. They all have to move together. So if you get any one thread that leaks out an address, you can deduce where the rest of them are. So, you know, it's, in a sense, this is security through obscurity. You're trying to keep a secret where you are, but it's not really possible to prevent that from leaking out various ways. In Unix processes, people often use fork to create a duplicate of the existing process and move forward, but if you do that, the new fork has the same memory layout as the previous one. So after you deduce one, you can deduce everything else that forked from it. All right, and then there's heap protections, which Microsoft has really gone to town on. Now remember, the fundamental problem with the heap is it's a doubly linked list. You have objects of varying size that are connected, so you put in the information about this object, and then you have a forward pointer that goes to the next object, and then to the next object, and there's reverse pointers to go the other way, so you can walk the heap both ways. And when you delete this object, you have to take this pointer and rewrite it to go over, and this pointer to go over, and that means if you were able to override the data here and change those pointers, the actions that tried to rewrite them will now be writing data you control to addresses you control. So the end result of this is that freeing an object from the heap gives you a chance to make an arbitrary write action anywhere in memory. And it's easy to take over the machine then, because you just write to some address that controls the execution. So that's the fundamental, the most common heap exploit is to attack free. So the simple answer is safe unlink. What this does, this is also what Cisco routers do, it walks the heap. So before you free anything, you make sure that the heap is still intact. See, so you walk the heap. You hop, 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 and then hop, hop, hop back. And if that works, then nobody has committed memory corruption and modified these pointers, and therefore it's safe to remove the object. This is very much like you check the canary before you try to return. From the pointer you see if there's evidence that someone has been tampering with it, then you know that you should not be performing the free operation because you can't trust it. It's been implemented in a lot of systems for a long time. Yeah, safe unlink is in there. The problem is safe unlink does not really end the attack. It just makes it more difficult, like all these things. There are several complicated techniques in the malloc maleficarium that goes on. You can exploit code that adds a chunk instead of freeing a chunk, for example. And there's a much simpler thing you can do. you can overwrite the pointers and very carefully arrange so that you can still walk forward and back through them, right? That you still can make a write. It's not 100% arbitrary, but you can change the values as long as you change them carefully. And it can still hop forward and back, but you still get to do a desirable thing when the chunk is freed. There's a look-aside table in early versions of Windows heaps, which is used to handle fragmentation on the heap, and there were some exploits that attacked this. It had no security checks there at all, and it was singly linked, so it was a good way to do it, but Microsoft doesn't use it anymore. They ended look-aside lists. They have something called a low fragmentation heap, which is pretty complicated. Microsoft heaps are much more complicated than Linux heaps. And now they have heap cookies. Just like you put stack cookies in, also called Canaries, it's got cookies put into each heap's chunk header to notice if somebody has been overriding the data in one heap and getting into the control structures in the next heap. The problem is, if the cookie check fails, it doesn't stop execution. It just does not free the object. So you can just run it 100 times. It doesn't stop the server. You can just go until you get lucky and you hit it. I guess until you successfully reproduce the supposedly random cookie. So that's pretty rude. In Vista and later, Microsoft tried to make a more effective random number. So you make 8 random bytes, which would be 64 bits of entropy, which is really a lot. You can't brute force a 64-bit number in any reasonable amount of time. Then they XOR them together, use other integrity checks, and then have some degree of randomization for the heap. And that's considered quite strong heap protection. But as you will see, it kept on getting exploited, and Microsoft kept adding more and more and more, which is still happening. So in Windows 8, they added about a dozen more things. Guard pages and exception handler removal and all sorts of stuff in Windows 8. And then you see safe unlinking has been around since Windows 7. They got more and more good defenses here. And then in Windows 10, they're going to add even more. Cookies in the kernel pool to protect jumping in, exploits in the kernel, a non-executable kernel pool, which should help prevent heap spraying, supposedly. And much improved randomization. Now, remember, one of the big problems here is computers don't have anything random at all. So you try to take the clock and the user input to make something random, and it's all pretty lame, and you end up with numbers that aren't really random. So, and that's, you know, that's Dilbert's take on this. I mean, how do you know if it's random? Here's the random number generator that says 99999, and they say, is that random? Well, it could be. You don't know. How do you ever really know if something's random? And how do you rate the quality of randomness and test it? Nobody really knows, but they got so fed up with it, they built a hardware random number generator in the Ivy Bridge CPU. Now, the general way you make an electronic random number generator is you run current through a resistor, and when you do, it has Johnson noise because the atoms move randomly in resistor from heat, and that causes the resistance of the resistor to vary slightly. So the current, if it's supposed to be 1 microamp, it's 1.01 and then 0.99, and it wanders up and down. And then you amplify the noise. And this always makes me think that there might be an attack that would involve putting your computer in a strong electric field or something. But anyway, this is a physically random event, not digital, that you amplify, and that's what they put in the Ivy Bridge CPU, which sounds good, but the problem is Edward Snowden came out and made people super paranoid, right, that the government is sabotaging everything. So the FreeBSD people refuse to use that generator because they say the NSA could have poisoned that random number generator and we would never know. Because, of course, you can't tell from the outside. And the problem is they did that twice. They got caught absolutely poisoning the random number generator in cryptography. And when I went to the TrustyCon, run by Mikko Hyponen, Bruce Schneier was there, who is, as far as I'm concerned, the only sensible person on stage. And he said, this is, the goal of the intelligence community is no bus, nobody but us. They want a back door that they can use that nobody else can find. And he said, if that's what you want, the smartest way to do it is to poison the random number generator. Because then nobody can tell you've done that, no matter how many samples they take, and you have some secret numbers to let you predict it, and if you really don't leak those secrets, you really have achieved nobody but us. We can get in, but nobody else.
They did that through some algorithm they published through NIST, right?
Yes, they put pressure on NIST, also RSA. It was one of the Diffie-Hellman versions. Had these constants they told you to use that they didn't explain, and it turned out Microsoft researchers figured out that if you use these constants to create the pseudo-random number, there are, in principle, numbers you could use to predict them. And maybe they poisoned it, and then they paid $1 million to RSA to bribe them into making it the default version of Diffie-Hellman on some of their products. And it was really kind of clear that they did poison it and then pressured people into making sure everybody used it. And you know, that's their job, right?
Well, even if that's so, do you think the guys at FreeBSD can do a better job?
Well, that they certainly could do something that hasn't been poisoned by the NSA.
Well, maybe.
But I mean, this is why I really like Bruce Schneier, because Bruce Schneier said, look, if you're going to work on Earth and sell products, there's going to be a government overseeing you. And there's an attack that you can't stop called coming in with search warrants and cops and lawyers to see what you're doing. And so you have to accept that somebody is watching what you're doing and exercising oversight. And who do you want it to be? The NSA or government of China, government of Britain, Chile? What do you think? He said, among adversaries, the NSA is a relatively benign adversary. Unless you're actually a terrorist, you probably don't really have to protect your stuff from the NSA. But anyway.
Unless they declare you a terrorist.
What's that?
Unless they declare you a terrorist.
There is that risk. But if you're living in America, you're totally at the mercy of the government deciding to blow you up at any time. I mean, that's what it is when you live in a country. They have cops and soldiers, and you know, that's you have to leave. And where are you going to go that you trust more? Maybe Finland or something, I don't know. But anyway, but you know, ultimately, living in the USA and doing business in the USA and imagining you're going to hide your stuff from the NSA just seems to me like a fundamentally illogical position to take in your life. Because their whole job is to penetrate all signals intelligence, and they are the smartest people in the world, and they have the most advanced equipment in the world, so it's not a very realistic plan to keep them out. Just like if you want to physically protect yourself from the US military, so even if the military comes here, I'll save myself with my shotgun. I don't think so, you know, I mean, I just don't get it. Anyway.
They did eventually get Osama bin Laden, although it took them a while.
They did, and the way he did it was no technology. You can go hide in a cave and only send messages out by talking to people. That's a pretty good technique, as long as all those people don't betray you. But very few people have followers that are that zealous to actually not betray you. He had the religion thing, which is how he did it. But anyway, so there's a lot of other attacks, and Windows 10 has a ton of new mitigations. They've added SMB signing and Kerberos to try to stop man-in-the-middle attacks. They've got this thing they talked about quite a lot, UEFI, checks the signature on boot up. They imitated the iPhone and the iPad on that to make sure the kernel has not been modified before it boots up to stop rootkits. And the same thing with bootkits here. They have Windows Trusted Boot that verifies components during boot to make sure they're not altered. You've got address space layout randomization and data execution prevention and many other integrity checks. If you download software, they've got their smart screen reputation thing, which turned out to be a huge political relations nightmare because it means every time you put any URL in your browser, they send it to Microsoft servers first to see if it's known bad. And everyone immediately said, Microsoft is spying on me. They see everything I'm doing. They're an evil company. And that's, you can't win for losing. You know, they have the most effective defense against downloading stuff, but it does mean that in some sense they are spying on you. And such is life. They got rid of the browser add-ons like Java and Flash, which is what everybody figured out is a lot better than trying to make those things safe. And if they try to run malware in Edge, they've got a bunch of other protection modes that put things in app containers, sort of like virtual machines, so that even if someone does exploit your browser, it supposedly can't get down to the system level. These are all typical defenses over and over, and I think a lot of these come from the blue hat contest. Like, see, Microsoft will invite you if you're a famous enough hacker, and they will pay you $100,000 to hack through their system, and they'll pay you another $100,000 to build the defense. And many of these defenses are written by the attackers that made the attacks. So that's pretty clever. I mean, Microsoft went from being the enemy of all security research and pretending there's no problem to just totally embracing it as they just sort of wised up and got a clue. Remember, I was at TorCon about 8 years ago, and Microsoft brought us all a beer, which was their first entrance into the hacker community. But they decided instead of like trying to lock up all the hackers, we're going to like be your pals. And that kind of worked out for them. Anyway, so OpenBSD and FreeBSD have their heap versions. They use this older version of malloc, and then switch to a modern one, mmap, which allocates randomly located chunks of RAM. So no two chunks will ever be adjacent. So even if you do overflow one chunk on the heap, you can't overflow into the next jump on the heap. That's the idea. It sounds like a pretty good idea. I'm not aware of any tests to tell us how well it works. So it's getting harder and harder to do heap exploits. People are more and more aware that the control parameters in the heap blocks should be protected from overflow from the data portion. And there are other ways to do it. But sometimes there's something else stored in the heap that's useful, like the vtable. It contains pointers. Pointers stored on the heap. And then there's the structured exception handler, which we exploited in a few of these attacks, where you can change the values that are used when an exception occurs, like a divide by 0. Back in the old days, Windows leaked the address of these things in a pointer, in a register, and now they automatically zero all registers before calling any handler, so the handler you write does not have any information about where things are. You can't put the exception handler in the stack. And PE binaries now whitelist permitted exception handlers, which is a really good idea. So you cannot change the exception handlers to point somewhere stupid like the stack or the heap. They have to point only where they're supposed to point. Sort of like register DILs is a defense in Windows against malware. DILs have to have only certain approved addresses.
So
Yeah.
They must do that just at boot up time, when they actually sort all this out.
Yes, unfortunately, the registry thing, you can actually change at runtime. So most of these defenses sound good when you actually look at them. There's kind of you can just turn them off and stuff like that. I mean, that's a problem. But at least they stop, what they do is they stop old attacks. All the old attack rules quit working, and you have to learn the new Microsoft defense and re-engineer your attack to get through. And that's all you can ever do, is raise the bar. The cops buy bigger guns, so the crooks get bigger guns, so the cops get bigger guns. That's all you can ever do. And the safe SEH, even if you do not have new code that was compiled with the safe SEH switch to get these fancy protections, it still has some protections. It has, the handler still has to be an executable RAM, and DEP helps block some areas of RAM, so some exploits won't work, but that's not a very strong defense. But really, you know, what can you do? If you're going to run legacy code without breaking it, you can't really put on too many strong defenses before you make it stop running. You really have to recompile the old code and get the new version of things pretty soon if you want to be safe. So there's exploitation tools. There's EEREAP, which will take a memory dump and hunt through it to find trampoline code, which is essentially what Mona did when we did it, to find useful code fragments that can be chained together. PDEST will freeze a process and look through the RAM image of it to find good trampoline code, which is handy. SEH Inspector will look at DILs and EXEs. A lot of these things seem to me like you can duplicate them in Mona, the way we've been using it.
Before we go on,
Yeah.
can we go into the concept of trampoline code a little bit more for me?
A translink?
Trampoline.
Trampoline code is very simple. So if I want to do something like turn off NX, I need maybe 20 machine language instructions. So I find a way to jump. So I have a DIL that has 1,000 lines of machine language, and then at the end it has like two things in a return, like a pop, pop, return. So I find a way to jump like 6 or 8 bytes before the end, execute just the last 2 instructions and return. And then I do that to another DIL and another DIL, and out of these little fragments I assemble what I want.
Okay.
So you write it in C, you compile it, it takes 20 machine language instructions, you figure out that it could be done with like 4 or 5 instructions for each one of those, and you then hunt through and assemble all these pieces, which is why it used to take hours to do this. But it's amazing that Mona can do it in about 5 minutes.
So,
They call them-
is trampoline code and chained execution the same thing?
Is what?
Chained
Oh.
execution.
Chained execution is one use of trampoline code. There are much simpler ones, which we did in one of the projects where all we needed was pop, pop, return, because the address we needed was just 3 words up on the stack. So that's a simple trampoline where you only make 1 bounce. We just needed to find pop, pop, return that was executable. And that's all we did, pop, pop, return, now you end up with, that's 1 bounce. But to turn off like data execution prevention, it was like 20 bounces. That's what Mona did, pop, 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 pop. You have to have these 10 addresses or 20 addresses lined up on the stack, so it'll do a couple instructions here, a couple here, a couple here, and that will all add up to turning off DEP. Yeah, that's good. That's all it is. And of course, the defense is incredibly simple. The library should just not let you enter except at the real start address. You shouldn't be able to jump in 8 bytes from the end of a library. That's so simple, and yet it took them a long time to figure it out. Anyway, all right, good. So we got the last batch of iClickers, which there's only 2. So which one puts function pointers in a predictable location? Which is, of course, a pretty bad idea. So another thing Bruce Schneier said once, which is deep and sensible, he said, security through obscurity is all you ever have. in principle, there is some secret that you have, which when found means it's all shot to hell. I don't know if that's true, but he's a very smart guy. It's certainly worth thinking about. Anyway, Linuxgate did that. Put pointers in a fixed location so you could find them. And which one of these may have been poisoned by the NSA? Well, I guess all of them, but anyway, one of them has been accused of this publicly. I mean, once you go down that rabbit hole, everyone could be a spy. They could have subverted my friends. There could be bugs in the wall. You go dig a hole in the ground and hide, you know. There was a good Onion thing, the Google opt-out village. Like, if you really don't like Google, what do? You sort of have this sort of village of people living like cavemen, hiding, starving to death with no air, because they're trying to make sure Google can't tell anything they do, and that would be really hard to accomplish. Anyway, well, if you go to China, they got the Chinese government totally is what you're doing. Which one is it? I think it's the Korean government with the Red Star, right? They put all this spyware in your operating system, so reporting back everything you do. And I probably, yeah. Anyway, so this is, I better be right, RDRAND, that's right. What's it? Yeah, it's in your OS. And in China, people certainly think they're going to poison all the hardware, put hardware Trojans and everything and know what you're doing. I don't know if they've done that, but I wouldn't be surprised. Anyway, let me save this. This is 127, chapter 14. All right.